All right, so let's implement a neural network in R. So the package we're going to be using implements neural networks with a single hidden layer, which is fairly limited, but good for exposition purposes, good for learning, good for kind of playing around with stuff. If you want to access more complicated neural network architectures, there are packages in R that allow you to use libraries like Keras, which is a pretty high-powered piece of technology. So I just want to point out that it's not as limited as what we might see today, but today is really good for just getting some intuition, building some fundamentals, and seeing how well these models can do, even when they're relatively simplistic in terms of what neural networks could be. What we'll see is like it's pretty darn good, even just by themselves. So we're going to be using a package called NNet, and if you don't have it, go to Packages, Install. That builds the neural networks. The other one we want is called Neural Net Tools. This is going to have the plotting function that actually allows us to visualize the neural network, whatever that is worth. So we'll see in a moment that is not as useful as one might hope. So again, Packages, Install Neural Net Tools if you don't have that package installed already. So the final thing we'll need to calculate benchmark error rate is our Babson Analytics source package. So teaching data analytics in R, Babson Analytics.R. And this things like benchmark error rate, this type of thing. Okay, so we're going to be working with the Boston housing data set today, and in particular, we're going to be trying to predict the categorical version of the median value. Is high val? High val, yes. High val, no. So we want to say read.csv users Nathan Karst Dropbox teaching data Boston housing. So hopefully this one's familiar by now. We're going to make a couple small amendments here. So we need to convert df $is high val to a factor. We need to get rid of median value. And there's not a good reason for this other than it makes it'll make the plot really, really messy. But rad is a categorical variable. No, let's just do it. Can't shy away from these things, can we? We'll see. And then you can make a decision going forward whether it's worth it or not. But it'll kind of be a mess, but a good mess. So we'll run all of these three things. Excellent. Okay, so we're going to do this wrong first, and we're going to show that what's wrong with the error rate, and then we're going to do it correctly, and then we'll see what's going on there. So the next thing we need to do is normalize or make our training test partition. I'm going to copy paste this code in. I just want to point out here that this is a little bit different than what we've seen in the past, isn't it? In the sense that there's not quite as many lines. It does exactly the same thing. It's just in a slightly different form. This is to say that there are many different ways to write an equivalent piece of code. So if you have an older piece of code that does a training test partition, by all means, I'm going to call this training just to be consistent and make sure that this runs okay. Great. Okay, so I'm going to build my model. Model equals NNet. And again, it's the same functionality, same kind of argument structure as anything else. The only thing is this additional argument, size equals 4. And this is like a bunch of different methods that we've seen. Like KNN, you have to specify the size of the number of K, the value of K, the number of neighbors. And other functions, you have to specify the size of various things or whatever. Here, it's just the number of nodes in the hidden layer. So here, our hidden layer, we have input, we have hidden layer, we have output. That hidden layer is going to have 4 neurons or 4 nodes in it. I'm going to build this thing. Oops, wrong line. There we go. Okay. And let's see how this goes. So let's do plotnet of model and see how we look. Okay, so this is a mess. So let's point out some things that can help. So here are our layers. We have our input layer, we have our hidden layer, and we have our output layer. Notice because we specified size equals 4, we have 4 nodes in our hidden layer, H1 through H4. Each one of them has a bias up here, and we have our bias for our output node here. Each one of our inputs is a different node, including dummy variables for rad. So this is the situation I was trying to avoid earlier. We're thinking about avoiding earlier. Notice that rad1 is missing, but every other rad is included. And basically we've just dummified this categorical variable into rad2 yes or no, rad3 yes or no, rad4 yes or no. This is often called one-hot encoding in the literature. and every other numerical variable is just seen here like it is. We have these edges, and they are black and gray. So the design paradigm here is that black means positive weight, gray means negative weight. The thicker the trace, the stronger the connection. So for instance, here is a weak negative connection between H3 and the output node, and the bias here is a strong positive connection between this bias node and the output, and so on and so on and so on. So you might be asking yourself, Self, what can I understand or glean from this network? And the answer is virtually nothing. Like, if you're looking at this and saying, I don't know at all what that means, how does, for instance, crime impact anything? It's like, it is not clear. And this is not clear with one hidden layer, right? And in deep neural networks, you might have 100 or more hidden layers that all feed into each other in complicated ways. And so in general, there is no looking at a neural network and understanding its structure. There is a very active area of research that is trying to overcome this problem, but as of yet, there's not very good tools for this. I'm hesitating because there are a very small number of exceptions, one of which we'll see, but for the most part, not super great. Not super great. Okay, so not much we can do with this, but we can make some predictions. So let's do predict. Let's do pred equals predict model test, and we're going to see what this thing looks like. So I've made my predictions, and notice what I have here. This is not great. I don't know what this means. We have just a bunch of numbers, and doesn't seem to be a lot of variability in those numbers. So I'm not quite sure what this is. But again, this is one of these situations where we actually need to specify a type. So just the reason for doing it wrong and then doing it right is if you look at it and it looks not right, like looks like there's something strange going on, there probably is. And so in that way, it's probably pretty important for you to look up the documentation and see what we mean here. So let's look at this a little bit closer. Table, pred. No, I should call this predictions, shouldn't I? I've called it predictions in every other video, so I should just be consistent. We'll say observations equals test $ is high val. Lovely. And then we'll do a table of predictions and observations and see what we see. Oops, I have to run that down. Okay, so this does not look good. Okay, I guess there's two pieces here, right? So notice that this is a character, but it doesn't seem to be too problematic. But notice that we're only predicting high value houses here. There's something strange going on. There's no low value predictions at all, which is really, really strange. So let me fix this while we're here. So I'll say as.factor. And again, this is not something you'll necessarily know until you look, but you can see that it's outputting ones, and that's good. I mean, category 1, that's fine, but it's a little strange, isn't it? So what's going on here? It turns out that we've intentionally missed a really important data pre-processing step, and that is that because neural networks activation functions are really non-linear, they can be really sensitive to big and small variables. So for instance, if one of these variables has a much bigger range than the other or has much bigger values than the other, it will swamp that activation function. Basically what the neural network just does is get inundated by this one strongest variable. Like think about the activation function is taking a weighted collection of the inputs and then applying a function, that activation function. If that weighted function is like 10 billion plus all of the other little variables, but that one variable is contributing 10 billion to that weighted sum, the other variables in that weighted sum don't matter. And so what happens is we end up getting very bad predictions because we're only listening to one of the variables in the model. So to fix this, we do all the same stuff we always would with variables and, for instance, distance-based algorithms. We need to standardize or normalize the data to kind of get around this. So this is a data pre-processing step. So I'm going to put that right before my data management step, and I'll say library caret, and then this thing is We're going to say normalizer equals preprocess, which is a function from caret. Caret is a library itself, and again, you may have to install that. Preprocess df method equals, and then there's a bunch of different methods. We'll do range first. So this really is a normalizer, meaning the minimum is going to be 0. The minimum of the old variable is going to be 0 of the new variable. The maximum of the old variable is going to be 1 in the new variable, and this is going to happen to every single column. So we run this thing. So now we have this normalizer model that will go through our data frame and normalize each column, but we have to do that. So we'll say df equals predict normalizer df. So what have I done here? I've built a normalizer that looks through the data frame, and for each column decides how it would turn that column into a 0 to 1 variable. And that's because my method is range. And then I've actually applied that normalizer model to my data frame. So notice it's 2 steps. Make the model, but don't change the data. Make the normalizer, but don't change the data. And then actually change the data. So if I look at df $crime, for instance, notice that now, and these are in scientific notation, that all of these values are between 0 and 1. And in fact, if I say max of df crime, I get 1. If I do min of df crime, I get 0. And that's true for every variable, whether I did indis or lsat or whatever you want. So let me just run all of this again. So I'm going to load the data, manage the data, partition the data, and build the model. I'm going to run the whole thing again. And notice what I get here. I get a much more reasonable looking prediction. And in fact, if I were to compute the error rate, it's now actually quite good. Hopefully, we'll see. May have spoken too soon. So we'll say predictions not equal to observations divided by in-row test. And we'll say error bench, just to give it a comparison, is benchmark error rate, training $ is high val, test $ is high val. Let's run these 2 things, and then hope that my face isn't over the top of it. What did I do? Misspelled predictions. I forgot my T. Excellent. So I'll move my face down here. So notice what we've done. The benchmark error rate in this data set for this particular partition is 0.41. So 41% of the time would be wrong if we were guessing the mode every time. And by building this neural network model, we've brought that error rate down to 11%. So we cut it basically in down to 25% of its original value, which seems pretty good. The pre-processing step is really important. If we had not done the pre-processing step, the error rate would have been exactly the same as the benchmark error rate, which is not a good situation to be in. And this is still true even if we run this kind of over and over again, we can get kind of comparable performance. So it's not just based on the particular training test partition that we arrived at. It's actually kind of a more robust thing. So, to me, this particular script that we've written is kind of a more advanced script because of a couple different things. One is that as you go through, the predictions weren't going to work the way you wanted, so you'd have to figure out the type equals class, but then even then it returns a character, so you have to return it as a factor. But then if you were to compute the error rate, it's like not good, and it's not clear why it's good, and you kind of have to go back to the drawing board again and kind of read up on neural networks to realize, oh, pre-processing is an important, normalizing or standardizing is an important pre-processing step for neural networks, so I need to build that in. But this is actually how data science works in practice. It's like, it is an iterative process where it could be the case that the first time you write a script like this, it just is not good or doesn't work. And you kind of have to keep chipping away at these things. And even now, we're not done, right? Like we could continue in a bunch of different directions here. This is a normalizer. Would a standardizer be better? What if I change this from 4 to 5? What if I did some other feature engineering, or actually did take out RAD, or I didn't convert CHAS, for instance? And that's probably probably not a great idea, but maybe I should have done that, and maybe that would change my. It turns out it won't, but maybe it will change my my opinion. Like maybe it'll actually change my. Change my opinion of how various houses should be high or low value or whatever. So there's always mountains beyond mountains here, but the point is that it's not always a straight linear path from us to the finish line. Sometimes we have to do this kind of iterative approach where we improve our code over and over and over again.